So this is using the Annihilator method or the differentials to solve for undetermined coefficients. So this is a different type of method instead of using in the previous ones. Um, it depends on the person. Some people prefer the other way, some people prefer this way, but you can see the difference. So you can see which one you feel more comfortable. In most cases, one or the other will make it easier. Again, it just really depends on the situation. Okay, so this time is, well, what if it's not equal to 0? What do we have actually equal to functions? Okay, so this kind of method, we're going to use something called the annihilation method, and it says literally what it says. We're going to annihilate some variables to make it simpler to do so. Okay. Now, the first process is we're always going to be using a non-homogeneous situation. Okay, so it breaks down to 3 different parts. If the right-hand side has just regular e to the x power, therefore this is going to be our annihilation portion. Okay. If it has an x in front, therefore it's going to be this portion. And if it has cosine or sine, it's going to be this process here. It obviously gets more depth as we go along. Okay. So what does this really represent? So according to the annihilation method, this is what's actually happening. All right, let me see if I can focus this. There we go. So a linear differential operator A is said to annihilate a function f if this is true. And that's the key goal we're going to end up dealing with. Okay, so you use a differential operator to do this. Actually ends up being the process. For all x, and that is A annihilates f if f is a solution to the homogeneous linear differential equation. Okay, so we're going to start from scratch and then go from there. Okay, so the first thing we're going to do is, well, how do we define a differential operator using this annihilation method itself? So all we're going to do is simply just, what is this going to look like? Okay. Okay. So this ends up being, well, the plus separates it, so we're just going to quickly just do each one individually then. All right, so according to our rules, the first part has, and we're just not going to even look at the 5s yet so far. We're just going to look at the actual variables. It has x to the e, so it's this situation. So this is a b situation. So let's write some couple things down. So in this case, k is going to equal to 2, and r is equal to -4. So when we go to this portion, it's going to be, for this part, d minus r, so d plus 4, raised to the k plus 1 power. So in this case, it would be 3. So that's how we do the operator. And then we do the same thing on this side here. So this is a sine or cosine function, so it looks like this. So again, we're just going to write everything down. So in this case, k is going to equal to 0, a is equal to 1, and b is equal to 3. So now we plug it into here. So it's going to be d minus a squared plus b squared, so 3 squared, all raised to the, we go over here, k plus 1 power, so k is 0, so it'll be first power. So simplifying this is just the first power plus 3. Squared, so 9. Okay. So now putting both of these things together, we will get this as the entire operator. Like that. So that will be our operator for each one individually, which is also the operator of the sum of f1, f2. Okay. So that's how we're going to do this type of situations, how we're going to solve using the annihilation method. Okay. But what I want to do now is show you how the methods comply. So let's use a method we did back in a while and then use this one to see how the differences of the apply goes to. So we do the chapter 4 approach. So the chapter 4 approach is going to be roughly the same for each one. So first part is step 1, you do the homogeneous part. So we do just set it equal to 0. And then, so our characteristic equation is going to be just that. So we get r squared is equal to 1. So we get plus or minus 1 as our portion. So for our homogeneous part, we have y, I'll just put h for the homogeneous part, is equal to c1 e to the x plus c2 e to the negative x. And we'll keep that to the side. Alright, so now we go on to the non-homogeneous part. Alright, so since, we're going to split up into two parts. So we'll do the e to the, or x to the e to the x part first. That's for this situation. Okay. So in this case, we have m equaling 1, and we have r equaling 1. And r is a solution to the characteristic equation. So therefore, this solution is going to be equal to x to the first times, and m is 1, so a1 x plus a naught e to the x. And now we do the other part, which is sine. So in this case, m is 0 and r is also 0. And it's not a solution. And m is also 0, so we have y2, I'll call it, is equal to a naught, or well, it's going to be different letters, but you'll see what I'm getting at. There we go. So therefore, our solution, and I'll put everything in terms of one single variable. Well, before I do that, let me do the particular solution. Put all this together. I'll just go down in variables. I'll get rid of the C. I'll go straight to D instead. Now at this point, you would take the derivative twice and then plug it back into here and solve for each one individually. That's a very long process, but it ends up coming down to such that, let's see if my answers are correctly. You get a is equal to negative 1/2, or 1/4, sorry, and b is equal to positive 1/4. D ends up being 0, I believe. And E ends up being negative 1/2. So after all of this work, now we get our solution portion, which is going to be the two constants of respectively to our homogeneous part, plus these four in the situation here. So what does that look like? So I'll distribute the x into here. So it looks something like this. I'll put it in parentheses to make it easier for the separation of what goes where. all of this would be the answer. Now, the question is, how would this look like if we didn't have to do this kind of process? Okay. So now let's look at the annihilation method. All right, so let's go back to what we have. Okay. So according to the annihilation method, we do two parts. We do what would the operator be here and what would the operator be there. Okay. So again, we'll just go back and do each one individually, just like we did in the last example. So in this case, k is equal to 1 and r is equal to 1. So this annihilation, according to our rules, would look like this. And this operation, just like the previous one, will, let's say, k is 0, a is 0, and b is 1 after everything, right? There's no e's and no x's. So it ends up being kind of nicely ends up being that. Or just simply d squared plus 1. Okay. Now, we have these two to be considered, which is what we just like did in the last example. But we also have to consider the operator on the left-hand side. Okay. So the operator on the left-hand side, so I'll just put that in the middle, will be d squared minus 1. Okay. So how do we do this whole process into what we were about to do? Okay, so what this is saying now, according to our rule, and I have my rule here, is the entire annihilation ends up equaling 0 of this multiplication. Okay, so this a of f of x portion basically is what are all the entire operators of each individual category. Okay, multiply together to give you 0. So what that means is on the left-hand side, we have the operator of the middle part, which we have here. So that's going to be d squared minus 1, okay, times the operator of e of x e to the x, which is d minus 1 squared, times the operator of sine x, which is this one here, d squared plus 1, all equal to 0. And now what we have to do is solve for this equation. Now the best part is, because it's equal to 0, we now have a characteristic equation. So we're just basically going back to the homogeneous part we did up here, corresponding to its characteristic equation. So that means every d represents just an r, respectively. So this ends up being just r squared minus 1, r minus 1 squared, and r squared plus 1 equals 0. So if we just set each one equal to 0, we get r squared is equal to 1. We get r is equal to 1. And this is going to be come back later on. And here we have r squared is equal to negative 1. Okay. So splitting this up, we get r is equal to 1 and negative 1. Here we just get r is equal to 1, just from there. Here we get r is equal to plus or minus I. So we get the imaginary part. Okay. So let's write down all our distinct ones. We have r is equal to 1, negative 1, and I, and negative I. Those are our four major portions. Okay. Now, this is where we also have to make sure. So here, we have a multiple of 2. So we have 2 1s, and then one more here. So this is actually a multiple of 3. So there's 3 multiples of 1s. R is equal to 1s. That's going to come back a little bit more important. Okay. Okay. Now, according to our operator and the annihilation method, this is saying that our first solution will be, I'll just make this one for easier, will be e to the negative x power. The second one, if you follow this portion, this format, is going to be e to the x power. Third will be x e to the x power. And then the fourth one will be x squared e to the third power. One for each multiple done there. And then the last two represent the imaginary numbers. Each one represents just a cosine and a sine. So now our general particular solution, or sorry, our general equation, not particular anymore, is all of these combined with each constant in front. So it'll be c1 e to the negative x plus c2 e to the x plus c3, and we just keep going. So again, how to find these constants, not as fun to do, let's just say, as the previous one, but technically still doable. Okay. So the good thing is here, I don't know if it's easy, but it's somewhat understandable how to find the particular solution and the variables in front of it. These will be a little difficult and tedious to do as well, because you would do the same thing, take the derivative twice and set equals 0. You can find your constants themselves, but it's kind of tedious. And same thing applies here. You'll eventually do the same thing, but it's much more variables and much more complicated. But if you're just looking for the general solution, two different ways to do it. One or the other could be beneficial for you as well to do. So let's try one more. So find the general solution using the annihilation method. Okay. So let's look at this portion. All right, so according to our rule, we have k equaling 1 and r is equal to 2. So therefore, our operator is going to be d minus 1, or sorry, d minus 2, because r is 2, and 2 plus 1, 1 plus 2 is 2, so squared. So d minus 2 squared. All right. The operator on the left-hand side is going to be d to the third minus 3d squared plus 4. And I'll keep writing this just to make sure you get notation purposes. Okay. So therefore, if we follow the same framework we did on the previous example, we will have this times this equals 0. And this becomes our homogeneous part, so characteristic equation. Now at this point we just got to simply factor it. One's already done for us. So r is equal to 2 with a multiple of 2. Okay, so this one we got to factor. And this is just me knowing that negative 1 works. You could do all the other way of factoring, but I'll use synthetic division to break it down. So we get r squared minus 4. Oh, I completely forgot about my 0. Start it all over again here. So 1, 3, 0. There you go. There we go. So we get r squared minus 4 plus 4 equals 0. And this one factors nicely to r minus 2 squared. So this has a multiple 2, and we found out they also had a multiple 2. So really, if you want to look at it, this is pretty much just r minus 2 to the 4th power, putting those together. Okay. So we just technically really have one equation, or one solution, with just multiple parts. Okay. So we'll have y1 equaling e to the 2x, y2 is x, e to the 2x, and we just repeat all of it down. There we go. And then the last one, y fifth is what this one was, e to the negative x. So our general solution, x now, is just all these with the coefficient in front. There we go. So now the last part is just pretty much summarizing this method. So using the annihilation method to actually solve for undetermined coefficients, and it's another alternative to do so. Okay. Which, kind of makes sense when we break it down even more. So if it doesn't equal to it now, well, what if this is a general one? So if you want to find a particular solution, they get a little bit more advanced. Same process comes into play, and if it's sine or cosine, same situation when it comes to the particular solution as well. But again, that's only if you want the particular ones, not the general, because notice here we don't know which one's which when it comes to the homogeneous and non-homogeneous part. And that's the main thing, is just like the previous example, we weren't sure exactly what this part represented based off of it. Here we can actually tell what would be the homogeneous and non-homogeneous. This one is unverified. But this is a nice little twist because it shows you how we can find each one individually if we just wanted just the particular one itself.